मेरा आसिफ है और मैं इस सेशन के लिए आपकी मेज़बान हूँ। सबसे पहले तो बहुत शुक्रिया आप सबका कि आप ना सिर्फ इस सेशन में तशरीफ़ लाए बल्कि वी अंडरस्टैंड कि आप काफ़ी देर से इंतज़ार भी कर रहे हैं, सो थैंक यू फॉर दैट। अगर आप में से कोई पिछले सेशन में मौजूद था तो उनको पता होगा कि कितना मज़ेदार था हमारा पिछला सेशन, किस तरह हमने कहानियों के देश में इतना ना सिर्फ सैर की बल्कि बहुत लुत्फ़ भी उठाया, ना सिर्फ छोटों ने बल्कि बड़ों ने भी। गुलाबी दादी आई हुई थी यहाँ पे। तो जो ये हमारा सेशन होने वाला है, इसमें आप कहकशाओं की झुरमुट में घूमने के लिए निकल जाएंगे। ये एक ऐसा सेशन है जिसमें आप गैलेक्सीज यानी कहकशाएँ, सियारे, सितारे, वो केक ऑब्जर्वेटरी के अंदर जो वन ऑफ द मोस्ट पावरफुल टेलीस्कोप्स हैं, उनके ज़रिए देखेंगे। और ना सिर्फ ये बल्कि डॉक्टर राजा जो एक यूसी सांता क्रूज में प्रोफेसर हैं एस्ट्रोनॉमी और एस्ट्रोफिजिक्स के और उस डिपार्टमेंट में चेयर हैं, उनसे आपको बात करने का मौका मिलेगा। जो शैडो साइंटिस्ट एक इनिशिएटिव है उसको भी हेड करते हैं, जिसका बुनियादी मकसद ही ये है कि जो स्टूडेंट्स हैं वैसे वो एशिया में हो, यूरोप में हो, अमेरिका में हो, कहीं भी बैठे हों, तो उनको वो मौका मिल सके कि वो ऑब्जर्वेटरीज जो दुनिया में बहुत बड़ी बड़ी ऑब्जर्वेटरीज हैं, टेलीस्कोप्स हैं, मुख्तलिफ साइंटिस्ट रिसर्चर्स काम कर रहे हैं, वो उनकी ऑब्जर्वेटरी रूम्स के अंदर झांक सकें कि वो कैसे काम करते हैं, क्या काम करते हैं। तो इसी तरह आज का जो हमारा सेशन है जिसके अंदर विद इन अ फ्यू मिनट्स हम स्टार्ट करने लगे हैं, उसमें हम पहले डॉक्टर राजा से थोड़ी सी बात करेंगे एंड देन ही इज़ गोइंग टू शो यू व्हाट इज़ द लाइक इन द केक ऑब्जर्वेटरी। सो इट इज़ गोइंग टू बी अ सेशन इन इंग्लिश और लेट्स स्टार्ट इन फ्यू मिनट्स। He is a professor of astronomy and astrophysics in UC Santa Cruz, and besides that he's also the chair of the Department of Astronomy in the UC Santa Cruz, and he also heads the Shadow the Scientist initiative, which basically aims to bridge the gap between the laypersons and the students and the scientists and researchers who are working in the laboratories. So as you can guess, the mission of his initiative very well aligns with the Lahore Science Mela, and he's doing it on a much greater global scale. So over to you, Dr. Raja.
Thank you very much, Mohsina, for the kind introduction. You can probably see three screens, three rectangles here. One of these is me sitting at home in California. One of them is Dr. Alessandro Savino, who is at UC Berkeley. But the telescope we are using is located in Hawaii. And I will show you some of the controls of the telescope. And, I don't know how much time we have, but during this time, we'll stay on the Zoom call. Happy to take questions about what you're seeing. Let me share my screen so I can show you the controls of the telescope. One of the things I want to show you first is maybe an image of the telescope. So let me go there very quickly. Can you hear me all right? Is my audio clear?
Yes, you're audible. It's all clear.
Thank you. Well, thank you for giving me this opportunity, Mohsina and Yasu and Sabi. I'm really glad to be talking to the at this Lahore Science Mela to so many of you. So thank you for making this happen. All right, I'll put to share my screen and as Mohsina said, we are running this thing called Shadow the Scientist. I'm just going to go to our website so you can see what this looks like. And some of the telescopes we use are shown here, the host telescopes. And tonight we're using one 10-meter telescope. It's an optical telescope located on the summit of Mauna Kea on the Big Island of Hawaii, at an elevation of about 14,000 feet, nearly 14,000 feet above sea level. Now, inside the control room of this telescope, one of the staff from KECK Observatory is there, and Alessandro is in Zoom contact with him on a different Zoom call. And Alessandro, if John or Michael are free to join this, they're welcome to, of course. I will introduce them. But in the meantime, I'll just go to the screens. See this. These these are the, my screen is full, and I'm sure you can see that on your screen. The screen is full of different GUIs, graphical user interfaces, that help me control, or help, in this case, help Alessandro control different components of the telescope and spectrograph. And I'll say a bit about what we're doing with the telescope. We are using this telescope to study galaxies. We are studying, Alessandro is studying small galaxies, much smaller than our Milky Way galaxy. These small galaxies are in orbit around our neighboring galaxy, the Andromeda galaxy. And all of these galaxies are located about 2.5 million light years away. 2.5 million. Now, for astronomers, that is not very far away, because one can study galaxies that are more than 1,000 times further away than that, billions of light years away. But I'm actually going to stop my screen share so you can hear the sounds of the telescope. Give me one moment, please. So just stop and reshare my screen. This time you'll hear the sounds as the telescope is going through various stages of its process. So these are the controls. Here is where some of the data are being read out. In fact, this thing that looks like has these diagonal lines. These diagonal lines are produced by the glowing of the Earth's atmosphere. But if you look carefully, you'll see a faint vertical streak. And this faint vertical streak is the spectrum of a star, a single star, in one of these small galaxies that's orbiting the Andromeda galaxy.
CCD readout.
It hears CCD readout complete. That means it finished reading out the silicon device. The CCD is a charge coupled device. It read that out. Not one, but there are 8 of these CCDs. You can see a pattern of 8, if you can see my cursor. What we are doing, we have a relatively large group who are studying this together. Alessandro, Dan Weiss, Marla Jiha, Evan Kirby, several others, including myself. And what we're doing is trying to understand how fast individual stars are rattling around inside this small galaxy that's orbiting Andromeda. By measuring the velocities of these stars, we can understand how much gravity they're experiencing, and that gravity is dominated by dark matter in these small galaxies. So that's what we're studying here. We're studying the dark matter content, but also we're also studying the chemical composition of these systems. Alexandra, I think you must be doing a slit mask alignment, so I'm going to go to that window.
Yes, I am just checking that the mask is still aligned.
So this is an align check you're doing. And so in this window that you're seeing on the left, in a moment, when the exposure is read out, and we do a little bit of analysis, and we try to make sure that the telescope, what we're doing is checking to see that the telescope is pointed perfectly before we take another sequence of long exposures. And when I say long, these are half-hour exposures, 30-minute exposures. Oh, something went wrong. Alexander, with the...
Yeah, I saw that. Let's see.
Let me check.
CCD readout complete.
So one of the things I notice is the grating is not in 0th order. So check is not going to work.
No, because it was just an automatic check. So
oh, I see. So
it went to 0 and then it went back to 7,000.
Do you want to do this manually, just as a final line?
I do see the CCD here.
Yeah, I do see that also. I don't know why
yeah, okay.
This is failed.
Hi Mike, I'll do a manual check.
You should be able to, if you close SAT, open a new one.
This one? Close or destroy?
Either one.
Okay.
Oh, I see. You think the alignment tool is messed up. And to the audience, I just want to say what you're seeing is a real-time experiment. So we have glitches, software glitches, just like you're seeing now.
And then is it a file or no? instrument or actions, one of those lets you, okay, go to actions, and then we'll find out an image, and then select the last one.
The very last one. I think it's later than that. Scroll down.
Because that's your calibration. Yeah, you have to scroll down.
Oh, okay. Oh, I see.
Yeah, 66.
Oh, there we go.
Thank you, Arthur.
Yeah.
I'm just going to send moves and we'll probably go to
I'm going to share a different screen, Alessandra, if that's okay? While you guys are doing this. Just a moment.
Okay, we're good to go again.
Okay, I'm sharing a different screen, Alessandra, just to display some galaxy images. I'm going to do that. Just looking for, there we go. I don't know if you can see this. Yeah, you should be able to see my screen now. I'm showing you some images taken of galaxies that are further away. These are about 50 million light years away. Andromeda is 2.5 million light years away. These are 50 million light years away. I'm going to just zoom out. This is like a sky map, just like you have Google Maps, and this is a sky map. This software interface, and you can see that just going to reload. It's being a little slow, sorry. But these, what you see here, are images of galaxies. I'm having a little bit of difficulty with there we go, much better. I'm sure you've all used a map when you have low bandwidth and it doesn't load properly. That's what I'm experiencing here, unfortunately. A little bit of low bandwidth. But these are images of real galaxies that are in the constellation, in the direction of the constellation of Virgo. Obviously, it's behind, well, much more distant than the stars that make up the Virgo constellation. But these are some very large galaxies. This is one of the largest galaxies, in our astronomical neighborhood, Messier 87. These are other galaxies. These are examples of elliptical galaxies. But you also have examples of spiral galaxies. I'll show you some. This is an example of a spiral galaxy. Let's see if I can show you some more spiral galaxy examples. Are these images showing up okay, Marcina?
I'm sorry?
Are the images showing up okay on the screen? These galaxy images? Are they visible?
Yes.
Yeah, for example, this is a beautiful spiral galaxy that you're seeing. It's actually interacting with a second galaxy. And in a different project, not the one that Alessandro is using the telescope for tonight, but in a different project, other collaborators and I use the same telescope, same spectrograph to take spectra of some of these galaxies and again to understand their chemical composition, how galaxies form, their cannibalism history. Galaxies cannibalize one another. Zoom out a little bit. In fact, if I zoom out a long way, you'll see that this entire patch of sky that you see here is about, if you were to pack in full moons, they're about 10 degrees by 10 degrees, and the full moon is half a degree. So you could fit 20 full moons across and 20 full moons from top to bottom, 10 by 10 degrees, so about 100 square degrees, 104 square degrees to be precise. And initially when first came here, this galaxy, the one I'm about to zoom into, is one of my favorite galaxies. It looks spectacular. It is one of the galaxies in the Virgo cluster that is interacting with a neighbor. There you go. You can see how distorted this galaxy is because of the differential gravitational pull of its neighbor. But it's also undergoing something called ramp pressure stripping, where it's like as it falls into this collection of galaxies, the pressure of the plasma that's inside the cluster is causing material to be stripped from it. So this is an example of how galaxies interact with their surroundings and other galaxies. Are we going to do a Q&A session with the group there, or what are your plans, Masina? What do you think? How do you think you want to proceed?
I think you could continue as you're continuing, because like I said, it's more like a visually inclined audience. So if you could show more of such live scenes from the observatory, that would be amazing, yeah.
Masina, I'm having a very difficult time understanding your audio. I can hear you, but your words are difficult to understand, just because of the audio. Could you please repeat one more time slowly?
Yeah, I'm saying that you could continue the session just as you are, because we still have some time. We'll continue it for 10 more minutes, and you could stream it as you like, so that's fine.
Okay, thank you. Let me know if I should go back to the telescope controls to show you what we are collecting in real time. So tonight, we are, as Alessandro is using this 10-meter telescope, the KECK telescope, we are collecting these spectra, and certainly happy to show you details of that. They were troubleshooting something a few minutes ago.
Now it's a good time. Now it's a good time. Now we're not going to touch the controls for another hour.
Okay, so the alignment worked out fine?
Yeah, it was good enough. You can see the stars here.
Yeah.
We do have stars instinct.
Oh, I see that. Yeah, I see that. This is a star shining through the slit, and I see the fine alignment very well. And if it's okay, I'll measure if you measure the C, it looks like it was about an arc-second.
Yeah, it's not the best the site has ever seen, but it will do the job.
Alessandro, do you want to? I'll stop my screen share for a moment if you want to take a moment to introduce yourself, because there are, science is definitely a team sport, and it's called Shadow the Scientists with the plural, because rarely do you see people working individually, work in teams. And I want to take a moment to introduce yourself. That would be terrific.
Sure, that would be a pleasure. Yeah, so as Raja told already, my name is Alessandro. I'm a researcher. I work at UC Berkeley, California. I am currently in the institute in a remote observing room, so I am operating the telescope from far away. And yeah, I've been in the field of astronomy for now about 7 years or 8 years, and my main topic, as Raja said, is looking at these tiny galaxies which are much smaller than the Milky Way, and we are looking at comparatively close galaxies compared to what most of the other astronomers used to do, and in fact we are able to see the individual stars inside the galaxies. And what I'm trying to do here, and most likely what my research broadly focuses on, is studying the chemistry of the stars, so understanding what are the chemical elements that compose the stars, and trying to measure the ages of the stars. And in particular, I look at very old ancient stars, some of the first stars that formed in the universe, and I'm trying to build the demographic of those stars and trying to understand how well we can tell the age of these stars, and then understand how these galaxies form. observing together recently for a few nights in a while, for example, with also other collaborators. And I'm here tonight operating the telescope, but this is an experiment that is engaging tens of additional astronomers. And so, for example, although I am the one taking the data, then someone else is going to do the measurements of the data, and in turn those measurements will be used by many other scientists, because each one has their own skills and their own capacity, and each one has a specialty that we bring together to the group to actually achieve the broader science goal.
Alessandro, thank you. And you did your early studies in Italy, is that right?
I did my early studies in Italy, and then I pursued astronomy graduate research in other European countries. I was in the Netherlands and in England.
So, and my own journey is I went to school in the city of Kolkata in India and went to college there as well. I studied physics in college, and then for my PhD, my master's and PhD, I moved to the United States, and I was on Princeton University on the East Coast. I have a few other images to show as well, if that's okay. Let me see. I wanted to show you some images that have been taken recently with the James Webb Telescope. But Mosina, if there are any questions from the audience about what we are studying and why, please feel free to pass them along to us.
If there are any questions, please raise your hand and we'll bring the mic to you. Please go ahead.
Hello, my name is Ali, and I have 3 questions. Number 1 is, what is an average age of a star? That's number 1. And number 2, is it true or is it... Hello, can you hear me?
I'm having difficulty understanding the audio, sorry.
I said I have 3 questions. Number 1 is, what is an average age of a star? Is that audible? Sorry?
Okay, average age.
Yeah.
The stars we're studying tonight, the average age of these stars is about 10 billion years, a little more than 10 billion years. The stars we're studying are quite old, and they are they're about the same mass as our sun. So in units of the sun's mass, their mass is about 1, maybe a little less than 1.8, 0.9. And they have been around for over 10 billion years. 10 billion, so 10 to the power 10 years, roughly speaking. That was one of your questions. What was the other question? Sorry.
The other question is, the stars or the galaxies that we're seeing now, is it correct to say that we're seeing their past, not their present?
Wasila, could you please repeat?
I'm saying the stars or the galaxies that we are observing from the planet Earth, is it correct to say that we are seeing their past, not their present?
That's correct. I think that is absolutely correct that when we study the Andromeda Galaxy, the light that is reaching the telescope tonight left these stars 2.5 million light years, 2.5 million years ago. So it is always the case in astronomy that we are looking in the past. In fact, it's always the case even here on Earth. When you turn around and talk to the person next to you, light and sound take a finite amount of time to travel from that person to you or vice versa. So we always experience the past. And when the person is next to you, that light travel time or sound travel time is a small fraction of a second. But when the thing is far away from you, as is the case for Andromeda and its galaxies, that light travel time is much longer than a human lifetime, in this case 2.5 million years. But it's an inevitable thing that we always experience the past, never the present, never the future. Our direct measurements are always of the past. This is even true on Earth, like I said.
If I might add, a great advantage in the case of the Andromeda galaxy, although 2.5 million years sounds like an enormously long amount of time, this is a galaxy which has been living for about 12 billion years at this point. hot these 2.5 million years. And therefore, if we're looking at the Andromeda galaxy, we can basically look at it as it is, very close to as it is right now. And if you look at much farther away galaxies, which are billions of years of light years away, then you are actually looking at a galaxy which is much more different. And those galaxies are now completely different than we were seeing them, just because the light took so long to reach us.
Yeah, that's a very good point. So 2.5 million compared to 12 billion. That's a factor of 5,000. So imagine if a person is 50 years old, and what is 1/5,000 of 50 years? 1/100th of a year, which is 3 days. Right? So if you look at the person and say, okay, here's a video recording of them from 3 days ago, they haven't changed appreciably in 3 days. If they're 50 years old today, they were 3 days short of their 50th birthday. People don't change rapidly on such a short time scale. So galaxies are the same way. If you're looking at something whose look-back time is 1/5,000 of its age, that's not a very significant, it doesn't change significantly during that time. Does that answer the question? I wasn't sure I heard the question properly, but does that answer the question?
Yes, you answered the question. My last question is related to the previous question, that if that's the case, is that also the reason that we are unable to see any alien life form till now? Because to them, it could be that they're saying the dinosaur age on planet Earth, because it takes light to travel from Earth to the other galaxies as well.
I'm going to ask for Mosina to please repeat the question because it's I couldn't understand.
I'm saying, my question is related to the previous question, because the light takes time to travel from one galaxy to another. So is it that
Your audio is much clearer, Mosina. We can understand you, but the other audio was not clear.
Yeah, he's going to write down the question for us and then I'll repeat it for you. So while he's doing that, I would ask you a few questions that I already have with me. And before going on to them, I'd just like to re-emphasize that this session was attended by a very diverse audience. We have middle schoolers, high schoolers, professors, teachers. So it's been quite an interesting one. So the first question is, why we are not adding Pluto in our solar system?
Mosina, one more time, please. Why is it that?
Yeah, the first question is, why are we not adding Pluto in our solar system? Could you hear me?
Sorry, the audio cut out completely. Please try one more time.
Okay. Okay, the question is that why are we not adding Pluto in our solar system? That why are we not recognizing Pluto as a planet?
Oh, I'm so sorry. The audio quality is it's fluctuating a lot. Is it possible to type things into the chat?
Yeah, we do that.
Sorry about that. I'm really sorry.
Yeah, we were just typing it, no problem.
Okay, I'm going to look at the chat to see what the question is. Why are we not adding Pluto? Why are we not counting Pluto as a planet in our solar system? That's a great question. Is my audio clear?
Yes, your audio is clear.
Okay. So, a decision was made by the International Astronomical Union several years now, well before the pandemic, that it was decided that Pluto should be reclassified as a minor planet and not as a planet. And the decision was really based on physics and based on practical considerations. What started to happen, the reason it was reclassified is because other objects were being discovered that had properties that were similar to Pluto's in in terms of how non-circular their orbits were and how far away they were from the Sun. There were these objects that were being found. Some were actually slightly larger than Pluto. And if you continue to call Pluto a planet, then those other things that were being found also needed to be called planets. But what they noticed was that these new objects that were being found and Pluto had significantly different properties from everything else in the solar system. So it made sense from a standpoint of physical properties. If you base classification on physical properties, or the orbits of things, their sizes, it made sense to say there are really two categories of things in the solar system. There are planets. In fact, even among the planets, there are two categories. There are what I call gas giants, 4 gas giants: Jupiter, Saturn, Uranus, Neptune. And then there are terrestrial planets, rocky planets, Earth being one of them. So the 8 planets in the solar system could break them down into 4 gas giants, 4 terrestrial planets, and then everything else was a minor planet, Pluto being one of them. So the practical consideration is planets in the solar system in a certain order. If you continue to call Pluto a planet, then you have to call these new things planets as well. And new things are being discovered now quite frequently. And they all are in the Pluto category of minor planet. They're not regular planets. So you have to rewrite textbooks. If you decide to call Pluto a planet, you have to call these other things planets. And since new things are being discovered, you have to rewrite textbooks every, if not every year, every few years. So practically, it makes sense to reclassify Pluto. It doesn't change anything about Pluto. Pluto is what it is, but it's just placed in a different category, where it's accompanied by other minor planets, not the classical planets. So why did the Sun take such a long time to complete a trip around the galaxy? The Sun takes about 200 million to travel. The Sun is located 25,000 light years from the center of the Milky Way. And so I'm answering the second question on the chat. So 25,000 light years is the radius of the orbit. So if you multiply that by 2 pi, multiply that by 6, you get 150,000 light years is the distance it has to travel. And if it were traveling at the speed of light, it would take 150,000 years. But the Sun is traveling at less than 1,000th the speed of light. So it's traveling at about 230 to 40 kilometers per second. The speed of light is 300,000 kilometers per second. So the Sun takes about 200 million years to go around the galaxy once. Okay, sorry. Should I keep answering the questions in the chat?
Yes, if you could just answer this one last question.
Sure. Last one is, if light takes time to travel from one part to another, is that the reason why we're still able to meet any alien life forms instead? Yeah, and they might be synchronized or age. That's certainly possible. So far, there's been no direct, as far as I know, as far as my colleagues tell me, there's been no direct evidence of alien life, intelligent life beyond the Earth. But certainly, depending on the light travel time, we could be receiving signals. The signals we receive, depending on how far away they're traveling from, they're certainly looking into the past. How far into the past depends on how far away, how far away the light emitting object is.
Yeah, so thank you, Dr. Raja. Thank you for answering the questions and for the entire session, which has been very enlightening for all of us, because we not only got to see the galaxies, but also about how you do the dark matter analysis and different chemical composition analysis. So that's it, I believe, and we just again like to thank you and everyone else, and it's been a complete pleasure for us to have you. So thank you, and thank you to the audience for joining us. If you would like to add some closing remarks, you're more than welcome.
Thank you. Thank you very much. the students in the room and for the teachers in the room, please feel free to contact me through Morsina or directly. And we run several programs for young people, so thank you very much.
Yeah, we will tell them about the programs, and we're also collecting the questions and send them onwards to you through email.
Okay, I look forward to that. Thank you very much.
Thank you so much, Dr. Raja. Thank you.
Okay, I'm going to stay on the Zoom call because we're going to continue our Shadow the Scientist session. You can see other people are joining.
All right, we leave.
Okay, thank you very much.